Thank you all for coming. I think you can hear me. It sounds like that. My name is Ed Brook. I'm a professor in the College of Earth, Ocean, and Atmospheric Sciences, and it's my pleasure to introduce our speaker for the distinguished lecture this evening, Dr. Julie Brigham-Grette from University of Massachusetts. Julie is a renowned Arctic scientist who's done a great deal of work on studying the history of environmental change in the Arctic, and she's going to tell us a lot about that work tonight. I'll tell you a little bit about her before letting her start that presentation. She did her undergraduate work in Michigan at Albion College and then went on to the University of Colorado to do a master's degree and PhD. After that, moving northward, she did postdoctoral research in Norway and in Canada, and then eventually moved to UMass as a professor, and she is now department chair at University of Massachusetts. Julie has done a great deal of work in a variety of settings. She's a dedicated organizer of scientific efforts. She currently is chair of the Polar Research Board and has organized a really large lake drilling program in the Arctic in a very interesting lake whose name I can't pronounce, and so I'm going to let her do that. Really has been a great force in study of Arctic change. So please join me in welcoming Julie to the stage.
Good evening, everyone, and thank you for coming tonight. I am very happy to be here, and this is my first visit to Corvallis, and I guess I'm in the Beaver Nation. I saw on a road sign coming in today, and I instantly had a kinship with your icon, your beaver icon, because when I was in first and second grade, I had buck teeth, and my nickname on the playground was the Beaver. So I know what it's like to have big teeth and get teased about it. So anyway, thank you very much. So it's a really pleasure to share with you the outcomes and a lot of the questions we still have about the Arctic. And I was very fortunate to be part of this drilling operation to explore Lake Elgagikyan in northeast Russia. So I want to tell you tonight about that exploration, why it's important, why the Arctic's important, and particularly some of the implications that have coming out of this work. It would be negligent of me not to mention that I don't do this by myself. I do this as a collaboration with many people, particularly from other countries. We made this a joint international program with Martin Mellis, who is the chief scientist from University of Cologne in Germany, Pavel Minuk, who is a head of the Paleomagnetics lab at the Nesri Institute in Magadan, and then Christian Korbel, who happens to be the director of the Vienna National Science Museum, with his efforts in looking at impact rocks. And so those of us as the chief scientists developed this concept for this lake and pulled off what I'm going to show you as some of the really interesting results from that effort. But again, there wasn't just the four of us that did this. This was really a team effort. And the pictures I'm showing you here are of, particularly here, this is the drill crew, both the night crew and the day crew, when we finally, as I'll tell you, drove through the sedimentary rocks of the last 3.6 million years and into the impact rocks. We'd actually achieved our goal, and we really celebrated. And this is a picture of all the Russian crew that supported us in the field in this really remote place. So I'm going to tell you a little bit about that. Now, what's interesting about Lake Elgagikyan is this was a project that took a long time to develop. In fact, my younger son is now 21 years old. He was 2 years old when I started this project. And So as far as he's concerned, this is my other life, is this lake that he can't pronounce either. But in any case, this was a long time coming, a long development. And we were able to time the drilling, the actual major logistical effort. And I must say, the logistics, by the way, were helped by CH2M Hill Polar Services. And I see there's a building down the road. The alumni building is named after them. So I have another relationship here with your campus. This happened during the International Polar Year. So every 50 years for the last while, we've tried to celebrate the international aspects of our science. So in 2007 to 2009, a broad 2-year period, we celebrated this, and this was a major milestone. This drilling effort was part of that. So just to share with you a little bit about what the IPY was like, with scientists in both the Antarctic and the Arctic working together to try to come together with some more understanding of how our planet works. So this little video I'm going to show you is to get you an idea of how exciting that polar science is. Thanks to Jeff Haynes-Stiles for that contribution. So why do we care about the Arctic? It's way up to the north. Who cares? We live down here. Why should we care about the Arctic? Well, we've just gone through one of the hottest years on record, all right? And many of what we've learned is, of course, as the Arctic and particularly the planet is warming up, not all of the polar regions and not all of the world is warming at the same rate. In fact, in New England, this is a graph, by the way, on the left-hand side here is temperature at 2 meters above the ground going back from 1835 to the present. And this is the temperature of Amherst, Massachusetts, where I live in Massachusetts. And you can see the ups and downs, the positive trend of the February temperatures, and look at where this year is. We had one of the coldest winters in at least this record, and if we actually go back and compare it to a lot of the late Holocene records, it might be in fact the coldest February in 500 years. Where's global warming? Why do we have politicians throwing snowballs around in Congress? This is why, because they're thinking about the weather and rather not about the climate. So we're concerned about what's happening. Obviously the East Coast went through something like this, but look what this guy says. You know, long term I'm worried about global warming, short term about freezing my ass off. And that's a lot about the East Coast, and that's certainly very different than what we see here out west of the Mississippi. So let me show you a little graphic, and this is from NOAA off their website. This is a graphic that shows a couple of really phenomenal things. First of all, here, let me orient you. This is parts per million carbon dioxide on this axis here. And down here we have the equator, the North Pole, and the South Pole. And this line that's jumping up and down is showing you the recorded carbon dioxide in the atmosphere over time. The blue dot here is in Antarctica, and from the Antarctica, and then the red dot here is from Mauna Loa. And so you can see that as the global mean, represented here, particularly in the southern hemisphere, goes up, rises over time, and here's the clock, 1994, 95, and so on. You can see the seasonal cycle. This is the life and death of the planet every spring and fall. We see CO2 going up in the northern hemisphere because of the decomposition of leaves and things in the fall, and then the CO2 goes down in the spring because we're using up the CO2 in photosynthesis. So the northern hemisphere, because of has a larger landmass, actually wags the dog, so to speak, in terms of the CO2. But you can see it rising and rising. And over here we see accumulating the regional record coming up. And you see the seasonal cycle from particularly Mauna Loa and that from Antarctica coming up through here. And so it gives us an idea of that seasonal cycle, but also the background mean is increasing over time. And in fact, as we rise up here to the top, just in the last couple of weeks, I believe, we finally reached a point where the seasonal cycle of CO2, although it had reached peaks of 400 parts per mil at different times, we now have a global average of 400 parts per mil. And we have not seen that since the Pliocene, since about 3 million years ago. And so here, just to prove my point, here now the record is showing, here's now where we are today, coming down back through 1800, where this is the Industrial Revolution, right around 278 parts per million. And here we are running ourselves back. And this is starting to take advantage of some of the ice cores. We have experts here on this campus that work on these ice core records. And we're going back through time, recording the atmospheric carbon dioxide in the atmosphere. So here we are 20,000 years ago in the last ice age, somewhere around 180 parts per mil. Again, see where we've come from. And then here we are now coming into the last interglaciation. And then as we come back and compress this record, we start to see the normal kind of range of carbon dioxide in the atmosphere with normal climate change, somewhere running between about 180, 280, 180, 280, 180, 280. And this goes back about 800,000 years. So it places the fact that we're at 400 parts per mil in pretty good perspective. We're way outside of the box by a long range. And this is what's really important, is to try to put that into perspective. Now, why do we care about the polar regions? Well, partly because the Arctic is warming faster than any place else on the planet. The planet is warming, but the Arctic is warming faster. And if we take a line, this red line from south to north, and go through the planet, and you can just look at the zonal difference in temperature, and you can see that in fact the largest temperature increases are in the northern latitudes. So who cares? We don't live there. That's up there. We're down here. Why should we care? Why do we care about the polar regions? Well, we do need to care for a couple of reasons. You know, we've had a lot of strange weather, and I want to acknowledge that this next couple of slides here I've taken from Jennifer Francis. She's kind of a rock star on YouTube on this topic, so I'll let you look her up later this evening when you get home. But we've had a lot of wacky weather. Whether it's flooding in the UK, we've had flooding in Alaska, in places where we haven't had flooding before, flooding in Europe. Greenland saw tremendous melt. Sometimes we have our extreme cold snaps that are happening, and even snow in the Black Sea. This is a joke. Are you awake? Just checking how much beer and wine you had before you sat down this evening. But even in Japan, I mean, I don't even know how the snowplows get the snow that high up when it gets like that. Now, and also look at this one. This looks like a normal beach scene, but guess what? This is March in Burlington, Vermont. Something's wrong here. And of course, we've had this extensive drought that's ongoing even now. And people in Texas who own boats are in trouble. But again, a lot of strange weather, and of course this extending drought now coming out into 2015. So what do these events have in common? What's going on? Why is the weather getting so wacky? And Jennifer talks about stuck weather patterns, and I really like her concept. It's a scientific debate that's going on in the literature and in the blogosphere. But Jennifer's point is that, you know, here, if you look at, here's the equator, here's the pole, we have the Hadley cell, this is how circulation, the warm air comes up from the equator, it rises, and eventually heat is transported to the polar regions over time. But you notice the slant of that atmosphere. There's a slant on that. And her argument is that, in fact, if we look at this normal gradient from the warm equator, very thick atmosphere, to a cold cold Arctic atmosphere, we have this slope. And what she's arguing is the Arctic warms up, the slope is less, and therefore something that has very narrow waviness here in the polar jet becomes somewhat lazy, like a meandering river. If you put a river across a steep slope, it pretty much goes straight. If you put a river, like you have here in the valley, on a very flat slope, it just goes back and forth. And so her argument is that not only is it becoming more wavy, but it tends to get more stuck in place, causing extreme weather events that seem to stay in place. So this was something that came out this winter. Go home, Arctic, you're drunk. So why is it waving around so much? What else is happening in the Arctic? Well, we know that the Arctic is greening. We see shrub forests moving into tundra. We see boreal forests moving out into shrub tundra. And parts of the Arctic are greening at rapid rates. We also see that parts of the Greenland ice sheet are getting warmer. And in fact, this was quite remarkable. For a couple of days in July 2012, the entire ice sheet was in the melt zone, which we hadn't seen. It had happened before, some 100 or so years ago, but we're now trying to see, is this going to happen often? Is this going to happen every year? What's happening to the Greenland ice sheet? And we can see that parts of the Greenland ice sheet are in fact beginning to melt at rapid rates. And there are scientists here on your campus who are really at the forefront of trying to figure out what's happening to the Greenland ice sheet. Antarctica is also suffering with the warming world, and with a particular warming in the West Antarctica here that's happening. And we know from a report, particularly as a result of the International Polar Year, we put together a report that showed that 7 out of the 12 ice shelves around the Antarctic Peninsula have either collapsed or in the process of collapsing. And we also can see that very warm water that's getting up underneath these ice shelves is starting to cause collapse and decay. And so we're seeing this at a rapid rate, particularly in Antarctica, but also in parts of Greenland, this is happening. And we haven't actually seen this much before. And particularly last summer, 2 major papers came out suggesting that in fact the Antarctic ice sheet was in unstoppable collapse. Now the premise of that is that in fact what's happening is that the ice shelves here, these red areas, which are floating areas of ice, actually buttress, they hold up the rest of the ice sheet. So just like you'd see a cathedral here, we have this buttress that holds them up, and if we lose the buttress, there's a problem. And we're basically starting to lose the buttressing effect of the ice shelves. And some of these places, particularly here in the Pine Island, Thwaites Glacier area, may in fact be on the verge of constant collapse. So here's a paper that just came out this year, again showing how these little ice shelves, this is the ice coming down out onto this ice shelf, floating in the sea. And if we lose the buttressing effect of that, we can get what is essentially a steep cliff in constant decline, and there's nothing to help support it. Just like we have this arc here, if we lose the buttressing effect, the building is going to fall down. And you're not going to be able to stop it. So we have rapid ice sheet retreat. And this is now being incorporated into climate models and was not actually part of many of the climate models, and particularly the sea level models that have come up before. So a paper that just recently came out by Pollard, Decano, and Ali just showed you that, in fact, what would happen with this new ice, that we have this what's called hydrofracturing, and the breaking up of the ice shelves can actually cause a much more rapid decline of the West Antarctic ice sheet. And so you can see here, time 0 with the pink ice shelves here, and then 50 years from now, a collapse of those ice shelves, and even of the Thwaites Glacier, causing potentially, not the ice shelves, but more of the ice sheet, starting to really contribute to sea level. So this could mean a much higher rates of sea level rise. And this has very important implications for our the coastal management of cities and towns. Even the US Navy, it's gotten their attention. They've got billions of dollars of assets within a meter of sea level. So we have to be mindful of what do these models mean. But more importantly, it means that these ice shelves and ice sheets are much more vulnerable to warming than we thought. If we just go back 30 years ago, many of us didn't even worry about these ice shelves. We thought they were very stable and that they were not susceptible to warming. But now we know much better, and the implications are getting more important. So those of us who do paleoscience, we work on looking at past climate change. We need to know what is the normal, natural change of variability so that we can compare how can we discern what is natural variability versus what are human-induced climate change. And we do that by working in the past, but particularly this figure here shows a proxy for global climate change. It's based on marine sediment cores from around the world, a set of cores, and it's just appropriately simplified so that these up and downs are, this is warmer is up, and blue is lower is cold. So this is smaller glaciers, very small glaciers, very few ice sheets on the planet, and these are very large ice sheets on the planet. So we can think about this glacial, interglacial, glacial, interglacial world that we've been in for the last few million years, and we can also think about this time back about 3 to 5 million years ago when we really didn't have very large ice sheets in the northern hemisphere. And certainly, there were large changes in Antarctic ice sheets in the past. And back in this time period, people have estimated sea level to be about 20 meters or 60 or 70 feet above present. So we can study back in time. The thing that I like about being a geologist is that we're like time lords. We can go backwards and forwards in time, much like Doctor Who. You know, she's a geoscientist, I'm sure of it. So, because we can look at scenarios of the past, reconstruct and look and investigate what were the changes like, and then try to understand what that tells us about how the planet operates, and then move into the future. So let's move into the future. Let's look at what we learned from Lake Elgagikyan. Now, what's interesting is many of us look up at the moon and we can see all those fabulous craters, and there's lots of craters on different planets. And they're fascinating because we think about the magnitude of the impacts that cause these large depressions like this. And they create really interesting features like these shatter cones and shocked quartz with all these funny, and then also particular strange mineralogies that have in them. Having an impactor hit the planet is unlike any process we have on Earth. It creates some very characteristic features. Well, we're very fortunate, I guess in some ways, that 3.6 million years ago, a large bolide, about 1 kilometer across, hit the Earth in northeast Russia. Here's the Arctic, Alaska, here's northeast Russia, and this is the Arctic Sea Pack, and you can see a little bit of Greenland here. And this is the crater of Lake Elgegikin. So this is a crater, it's about 20 kilometers across. The lake sitting inside it is about 12 kilometers across, and it dates to 3.6 million years ago. So we identified this as an actual world-class target where we could learn tremendous amounts from the climate change by the sediments that are accumulated in here. And it also turns out this is one of the few places in the Arctic, across the Siberian Arctic, where there weren't large ice sheets to erase all the evidence of what had happened in the past. So it turned out to be a very relatively unique place. Again, it's dated to 3.6 million roughly, and we've done some seismic work to figure out where would be the best place to do the drilling. And I have to say, it's actually a whole nother hour to tell you about the details of how we actually pulled off our first drilling operation. But I had about $50,000 to go try to do this, to see what was there. And at the time, it gave me about enough money to get there but not come home. So I was, so I was able to get some collaborations with German colleagues who actually had enough money to make it possible for us to go there, get our first cores, and then come back together. So I also want to acknowledge with this is Dr. Olga Glishkova. I was standing in Olga's office in 1992, and we were, with her broken English and my awful Russian, we were talking about glaciations of Chukotka and comparing that with Alaska and so on. And she showed me a picture of this lake, and she goes, "Julie, we should core this lake." And I said, well, I'll try to get some money, we'll see what we can do. And long story short, it took me a long time to develop this, but we started to build a collaboration, convince people of how this was worth it, it's high risk, but they'll pay off. I actually acquired a pretty good, I have really like good vodka now because of all my trips to Russia, negotiating this operation. But we pulled it off, and it was really a wild dream to actually have an idea and do the field work and then actually make it happen. But some of the challenges were really quite formidable in the sense that we had to build a drill rig to operate at -30 to -50 degrees. And we had to build it in Salt Lake City and take it to the lake in Siberia. Okay? So, so this took a lot of planning, a lot of meetings. We set up first in 2008, we set up a field camp with our Russian logistics manager. So this is our camp where there's an outhouse right here with a person waiting in line. An outhouse at this end, cook and science quarters in the center, and then sleeping. And this, in fact, is a banya where you just throw water over your head and get a bath once in a while. So we actually had pretty cushy accommodations there on the edge of the lake. But we also then had to move the drill rig and all the other science equipment, and this required sending 2 containers across on the Siberian Railroad to Vladivostok. That then met 15 containers coming from the United States out of Everett, Washington. They met in Russia, and 1 week later, believe me, through Russian customs, we got all this equipment on a barge and sent it on the last boat going to Pivik. And this was really a great feat because of our connections with the Far East branch of the Russian Academy of Sciences. So really credit them with helping with this. And then there were the logistics of getting to the last part, and then here's Pivik up here. Okay, we get everything landed there, sent to this offloaded here. But then we had to wait for the ice road to freeze. Now there's a gold mine down here owned by a Canadian company, and they ran a winter road that came up from here around to Pivik. So we had to wait till the coastline froze in January and February of 2009, and then trucks took this, and you can see the road here. I hope you can see the road. There's a truck right there for scale. And you can see it coming down this road, and then this is a summer road, not plowed in the wintertime, just windblown, where the trucks came across, and then the last famous last 90 kilometers was this. The trucks had to be pulled through the snow by Russian bulldozers, 90 kilometers to get everything in. So we had 18 20-foot containers. And NSF, National Science Foundation, said, I don't want to see the tundra torn up for that 90 kilometers. So we had to do this so that we didn't leave a mark on the landscape. So we then set up our camp on the edge of the lake and waited for the lake to freeze over. And then once it gets to be about a meter thick at the end of January, you can get a Russian bulldozer out there, clean off the snow. And then we had Canadian ice engineers come out and thicken an ice pad for us. Now let me just show you what that involves. It means you clear an area about the size of a football field with a bulldozer, and then they take pumps like this, put a hole down through the ice, like you're ice fishing through a meter. You pump the water up and you make a thin film of ice. And over about 3 weeks, they thickened the ice platform, again, about the size of a football field, to 2 meters. This gives you a very rigid platform on which you can then put the drill rig, which weighs 100 tons. So the last thing I wanted was to be known for losing all that equipment into the bottom of this lake. And these ice engineers, I want to say, this is EBA Engineering in Edmonton, Alberta. They are famous, you may not realize this, but they are part of those ice roads, the ice road truckers you hear on the History Channel. That's the same company. So they build those ice roads that go up into Arctic Canada. They were fantastic. Building this at minus 50 degrees and partially in the dark was a challenge. Nobody thought, okay, you have an extension cord for the power tools to put this together. Nobody thought, oh, the plastic is brittle at minus 30 degrees. So when we opened up the electrical, all the power cords, they fractured, and so a lot of this drill rig was put together by hand because the power cords wouldn't work. So that was a big challenge. So just to give you an idea of what it was like, let's see, where am I going? There, just a minute or so of this, of the helicopter. All of the heavy equipment was brought in on the containers, but we relied on these Russian helicopters for getting in. I apologize, this is a little pixelated, but it gives you an idea of the crater as it looked here in the wintertime or pretty early spring coming in. Here's the camp. And so all the personnel came in and out of the camp with this. It was the only helicopter in Chukotka, honest to God. So we had to rely on this one helicopter to come in once a week and brought fresh vegetables and a few other things, but not tremendous amounts of supplies. The other thing that they did was they took the core material that we were collecting and took it out to keep it under control and keep it safe. So here is the camp, way back, this little dark spot here on the image is way back here, and here's our ice road, 7 kilometers to come out to the ice pad. We had an emergency shack here, and just in case it did crack and go through the ice, we had a place to run to be safe, and of course you have to have an outhouse somewhere out there. So we had, it was quite an expedition to pull off. So here's what we drilled. Here's a cartoon of the lake. Here you see the lake itself, the Quaternary, the last 2.6 million years of lake record, and then into the Pliocene, which is from about 2.65 million to about, in fact, the time of the impact here at 3.6 million. And then we actually drilled another 200 meters into the impact breccia for the impact community, because this was also a unique target rock for people interested in how the Earth materials respond to impacts. So I'm only going to be talking about the upper part of that. Now, how do we date this? You get this 500 meters, say 1,500 feet of mud. How are you going to tell how old it is? Well, one of the primary ways we looked at was looking at changes in the Earth's magnetic field, which can be recorded by the sediments themselves, by the magnetic minerals. So here is what we call a U-channel, and here's the sediment core, and you can actually measure through time, going down through here, changes in the Earth's magnetic field, and we know from other places on Earth that the Earth's magnetic field has been normal coming with the magnetic field going into the North Pole, and it's reversed many times. So these black and white signals here should tell you about those times of reversals of the Earth's magnetic field. So these black dots here give you the tide points based on the Earth's magnetic field, and we use that as the primary method for determining the age of the sediment cores. And then there were some other proxies that we used for comparing this record and then trying to figure out the ages of the material in between each of these dots. Now, the other thing that we do as earth scientists is we work with proxies. In other words, we can't actually measure, like with a thermometer, the past temperature of climate change in these cores. That's not possible. So we have to find other things that tell us about the temperatures and tell us about precipitation. And so a proxy is something that takes the place of something else. So we can use diatoms or pollen, the pollen assemblages that tell us what kind of trees and what kind of plants were living around the lake. What does that say about seasonality or the time or how warm the summers were? We can even look at plant leaf waxes or changes in grain size, and these new biomarkers that can tell us something about what was going on with the organic matter in the lake. And what paleoclimate scientists do is we produce a lot of wiggles, and these wiggles are often colder to the left, warmer to the right. And so we can produce these wiggles over time, this going back some thousands of years, and compare these wiggles of different proxies telling us different things, and then put together a scenario like a CSI investigation of what was the climate change like? How did it change? What was the seasonality? How warm did it get? What were the climate extremes? And so whether it was warmer or colder or wetter or drier, we determine from assembling all of these different kinds of proxies. Now, this is actually a real chart that we published. It has a lot of different proxies. I don't expect any of you to understand what that is because it's too much. It goes from 0 to 3.6 million years. But we use data like this. For example, this green wiggle going up in here gives us an idea. It's a ratio of silica to titanium, and in a simple way, it gives us a sense of productivity. In warmer climates, there's more productivity in the lake. There's more organisms and algae living in the surface waters. And in cold times, there's less. And so this gives us an idea of warmer and colder just based on that. So that's just an example of some of those proxies. Now, one of the things that's I wanted to show you in particular was how pretty these sediments are. I really love the look of these things. They're really interesting. In the Pliocene, we have a lot of really laminated sediments like this, and these are not seen in the younger Quaternary record. And in this one, we call our glacial facies. In other words, when the lake itself was permanently frozen over, even in wintertime. So imagine that Lake Elgagikkan was similar to the lakes in Antarctica that never have ice, they never thaw out. The lakes in Antarctica, many of them are frozen over the year round, and that's just what this lake was like. So we've studied a lot of those lakes in Antarctica to find out what we can learn about how they operated. And this facies here occurs for the first time at about 2.6 million years ago. It's not found in anything prior to that. But what we're particularly interested in are the fact that we have these really reddish laminated sections which are extremely warm. Every proxy we have in those are really warm. It tells us it's warmer and wetter in the past. So when we find these really kind of red laminated sections, they tell us something is really extreme. And we've supported this with pollen to show that in fact during many of these events, when we see these kind of sediments come back, the forests have come back around the lake. And so I'm going to elaborate on that here just for a minute. So now we have in general an image of climate change of the planet based on this curve. This is an iconic figure that gives you, it tells you the changes in temperature at the bottom of the ocean over time. And again, just think of it simply as warm is up, down is cold, and you can see, and this is regulated perhaps in part by carbon dioxide in the atmosphere and many other complex things, but you can see if we go back 5 million years ago, we have a little bit of variability, it's quite warm, and then we start to get larger changes as we get into about 2.5 to 3 million years ago. We're starting to get into the transition of the ice ages. And we start to see these swings in glacial interglacial change getting larger and larger and larger and larger. And we're going from a high CO2 world, when CO2, carbon dioxide in the atmosphere, may have been in the range of 350 to 400 parts per mil or higher, down to a world when we have the 180, 280, 180, 280, 180, 280, which is what this is back in through here. So we want to compare this and find out, how did the Arctic change? This is a global curve. What was the Arctic like? How do we go from a forested Arctic to tundra? And what factors cause these super interglacials, these warmer periods? And what does that tell us about the future? Are we heading into a super interglacial right now? We know that over time, this is the same curve up here. And then down here, I just want to point out, this is 5 million to the present, and all these different colors are people's estimates, different scientists' estimates of what was the carbon dioxide like in the atmosphere in the past. And there's a lot of variety. The science community is still struggling with what is the best way to measure this. The black line here is what we can measure from the ice cores from Antarctica. So we know that that fossil air is true. That's our best record right in there. And then you see that this is kind of a mess as to how we interpret past carbon dioxide. But generally speaking, somewhere in the higher range is what most scientists are thinking is what was true in the Pliocene time, at the time of the impact. So I'm a geologist. I think I'm more of a stratigrapher, and and I've been working for a long time on the Arctic. And there are a number of sites throughout the Arctic. I started working up in this region, and all these numbered sites are places where, in the Pliocene, forested conditions went all the way to the Arctic Ocean. And so at the time of the impact, we didn't have any Hudson's Bay. We hadn't eroded out this environment, and that means that this continental environment, where we didn't have inter-island channels, had a more serious continentality, which would easily allow forested conditions to reach much farther north than they are today. And so this is what the environment was like at the time that this impact occurred. And so a lot of the very warm conditions we see here are consistent with some of these other additional sites around. And we think that the opening of Hudson's Bay and the inter-island channels here was a result of the very first glaciations, that the inter-island channels were a product of glacial erosion. Now, so just thinking about, how did we go from a forested Arctic? If the Arctic was forested, how do we get to tundra like today? Now, so there are specialists around who study the pollen and look at what those assemblages of pollen say about what was living around the lake. And these diagrams can be rather complex, so I have simplified them down to these bars here. And here's some pictures to help you understand what is a mixed cool forest, or a cool conifer forest, or taiga, and then coming out into tundra down through here. And you can see at 3.6 million years ago, we had pretty warm conditions with mixed cool conifer forest. And at this end, we have tundra. So you can just think about time going back and forth through these various times. We have a cold spot there, and coming back and forth through here over time up to the present, escalating from forested conditions to tundra over time. Now what I'm going to do is take this record and flip it up so it's like a sediment core. So you can think about that. These are some major transitions. So here we're going to flip this diagram up on its end. So here's the bottom at 3.6 million at the Lake Elgagikyan, up to 2.2 million. And you can see the transitions here, the ideally thing. And you can, again, going back and forth. And here Pavel Tarasov has taken and produced a measure of landscape openness. So whenever the line here is over on this side, we have forested conditions gradually coming to tundra conditions. And you can see it's really complex. It's not like it just changed overnight from forested to tundra, but it is in fact very complicated. So I'm really looking forward to what we can do in the future to try to understand those transitions and all of the other climate change that happened in other parts of the world and what this meant for that. But you can see the general trend is there, but it was really complicated. The other complicated story here is, here again is our general climate proxy for the whole world. And I just want to show you here in Lake Elgegikin from, this is 3.6 million to 2.2, somewhere around 2.7 million years ago, we had a radical change in precipitation. We went from 3 times precipitation, what we had today, to much drier conditions. And the only other time that it gets that wet in Chukotka is when we have these super interglacials. So we're trying to understand at the same time, we can see these red lines show you today's conditions. We can see that, in fact, all through this time period from 3.6 to 2.2, most of the time, summers were much warmer than present, all the way up even to 2.2 million. So it's, for some reason, at 2.7 million years ago, the relationship between wetness and warm separated, and we went to drier and warm at some point. And so we're trying to investigate, is that just the result of the onset of Arctic sea ice? What are the conditions, what's going on in the Earth system to cause a major change in precipitation at this latitude? And we can take the summer index, this is our summer temperatures up here with the Holocene average. We can put the global marine stack on top of that and see that, in fact, our summer temperatures are tracking relatively well with some kind of global signal. So this is telling us this lake is just not a lake in Siberia that nobody could pronounce, but it's actually a lake that's recording a global signal. And by comparison here, we can see the best estimates of global sea level, plus or minus 20 meters back or here, going up and down here, you can see. And then we get larger changes in sea level over time recorded in parts of the world. Now, just let's step back for a minute. 20,000 years ago, sea level was about 125 meters lower than today. And that's because of evaporation out of the oceans and precipitation on ice sheets, and then the ocean, that moisture is stored in the ice sheets and sea level drops. So we know that when sea level drops, we're building glaciers, we're building ice sheets. But even here, even after this 2.7 million years ago, even up to 2.4, 2.5 million years ago, sea level is only oscillating at about 60 to 80 meters or so. So we're not building the ice sheets that we had 20,000 years ago, but we're starting to build ice sheets. So the onset of glaciation in the northern hemisphere is all partly wrapped up in this investigation. And how can this work contribute to other scientists' work thinking about how the Arctic became a glacial interglacial landscape? One of the things that we tried to do is do some modeling. Now, you know, we don't have an extra planet nearby where we can, you know, go over there and change the carbon dioxide and play around with it. We have to use the one we have, and the experiments we can play with are, in fact, climate modeling. And so what we can do is build a simulation, mathematical simulation of the Earth in a computer, and then we can change different tweaks of different things. And what we've done here is, on this panel, the top one, these three are all the same thing, but this one is a world with 200 parts per mil. This was 300 parts per mil, and this is 400 parts per mil. And what we did was we ran simulations with this being cold orbits and this being warm orbits. And what I mean by that is, you know, that the glacial interglacial change is largely dictated by the changes in the Earth's orbit around the sun, and both the shape of our orbit and also the tilt of the Earth and so on. So we have simulated here what we call cold orbits on the left and warm orbits on the right for a Pliocene world. And what we see is, what's particularly important in this experiment is that at 200 parts per mil, we see the Arctic is pretty, these blue colors are tundra. So at low CO2, you get tundra pretty easily in either cold or warm orbits. At 300 parts per mil, we get pretty large changes. Here, more tundra, less tundra, or no tundra. But at 400 parts per mil, we get tundra in both warm orbits and cold orbits. And that's exactly what we see at Lake Elgegikin, is that in the Pliocene, whether it's a warm orbit or a cold orbit, we keep the forests around the lake for most of that time, up until about 2.7 million years ago. So it would seem that the best explanation for these warm conditions was we were at 400 parts per mil, or at least in that range, somewhere around there, very warm, high CO2s. So that's the best explanation we have for why we had forested conditions back then. Now, another thing I want to point out here is that also our connection with our Antarctica. Now, in 2009, a major drilling project in Antarctica produced a paper that showed the vulnerability of Antarctica to deglaciation. And so what I'm going to show you are the comparison of these two projects, one in the Antarctic and us in the Arctic. In Antarctica, in Andrill, here on the West Antarctic ice sheet right here, there's a little dot where they took the core. And here's the drill rig sitting here in the open ocean, and when there's no ice sheet, no Ross ice shelf, you get this diatomaceous ooze. So here is a reconstruction of what that looked like, no West Antarctic ice sheet. But when the ice sheet advances and is nearby, you get this transitional material, and then when the ice sheet advances way out to the shelf like this, you get glacial diamictons. So I want to emphasize in the next couple of pictures that the diatomaceous ooze, when the West Antarctic ice sheet is gone, we have this yellow patterned sediment. And I want to just show you the coincidence between that. So this particular record tracked the behavior of the West Antarctic ice sheet. The most important part of this was that we didn't realize the West Antarctic ice sheet could come and go as easily as it has in the past. So here, what I've done, if you just focus, this is that summer temperature again from my lake, Lake Elgagickin in the north, and from 3.6 million to 2.2. And on the bottom is Antarctica. So these yellow areas are times when, through this pattern, when there was no West Antarctic ice sheet. So what this phenomenal record showed us was that the West Antarctic ice sheet could come and go during this period. It was coming and going. It was much more susceptible. And it turns out that some of our super interglacials maybe correspond to some of these times when the West Antarctic ice sheet collapsed. So you notice that I haven't drawn these lines exactly to match up because I'm not sure. There are a couple of uncertainties in the age of this chronology here, so this is where people working on that record and I can get together and try to see if we can match these up. So again, here is Lake Elgagickin at the top. The red areas here are super interglacials from the present back to 2.8 million years ago now. As I've switched time frames on you. So these little red squares are times when we have super interglacials, very warm conditions. The forests come back around the lake. Again, it's all tundra today, but the forest came back. And it turns out that and this is Antarctica down here, these yellow areas are times when the West Antarctic ice sheet disappeared. Now, it turns out our best match is right here at about 1.1 million, where we have the best chronology. We can see that the West Antarctic ice sheet disappeared, and then about 11,000 years later, the Arctic was warm because of this, again, this orbital forcing that we can see. And so what we're suspicious is that all 17 of our super interglacials actually correspond with a time when there was no West Antarctic ice sheet. So we're exploring this right now. I'm not going to say it's absolutely true, but what it looks like is that these match up reasonably well. So if we go to these three areas, this time about 1.1 million years ago, this time here about 400,000 years ago, and two other examples in the next frame, I'm going to show you here again. This is, again, this earlier time, and then the most recent. This is 20,000 years ago to the present. This is July temperatures. Here, not very warm. This is 125,000 years ago. Again, not very warm at the lake, but during this time, 400,000 years ago and 1.1 million years ago, it was really warm. We were in the super interglacial in the Arctic, and we had very high precipitation. Now, if you talk to those people who are working on the geology of Greenland, the best estimate, and there's lots of different figures for this, but I'll just throw this one up. It's not too bad. That we know that 125,000 years ago, sea level was higher than present, about 6 to 9 meters above present. And we think part of that, at least a couple meters, came from a smaller Greenland ice sheet. When the world was a little warmer than now, because we were in a different orbit, not carbon dioxide, but because we were in a different orbit. And if we go back in time to this time and this time, when it was even warmer than before, we can't help but think, does that mean that the Greenland ice sheet completely disappeared during these intervals? In which case, we have this notion that not only can we get rid of the West Antarctic ice sheet, but in fact, if we warm the world a little bit, we can actually get rid of Greenland. And it's happened before. Now, it hasn't happened because of carbon dioxide. It's happened because of these other orbital parameters. But what's happening in carbon dioxide in our world today is actually increasing the temperature of the entire planet and basically causing the same forcing. So we're trying to look at mechanisms for why this happens. We're thinking about ocean circulation with warm currents transferring up into the North Pacific, or changes in surface waters and how they translate around. How does the world ocean, the ocean conveyor belt, communicate in terms of transmitting heat from the the tropical regions into the polar regions? So this is an area of research of trying to figure out what is the connection between what's going on in West Antarctica, or particularly in the Antarctic here, and how circumarctic bottom water may translate into what's happening in the Arctic. These are investigations that involve both atmospheric scientists, oceanographers, and geologists to try to come together with how to understand how this all makes sense. We have at least a notion that, in fact, if you change the sea ice regime and melt the ice sheets or melt the ice shelves in Antarctica, then in fact we decrease the production of Antarctic bottom water, these cold waters that circulate up into the North Pacific, and maybe then change the stratification of the Pacific, and then maybe cause a slight warming. But there's issues with timing, there's issues with mechanisms, and this is kind of an area of active research that we're working on right now to try to understand how does this record in Antarctica and the record in the Arctic make sense together. And we're trying to look at, again, these 17 different interglacials, what was common about them. These two guys are Rob DeCanto is a paleoclimate modeler, and this is one of his grad students working on look at what are the common mechanisms, particularly orbitally, and then also in oceanographically that we can connect. Is there some unique solution that explains an extremely warm Arctic? Why can we melt the West Antarctic ice sheet and then grow forests again in the Arctic at many times in the past? So we're trying to figure out, what is it? Is there a way that the orbital forcing here, again, the shape of the Earth's orbit around the sun, changes in that orbit, can precondition both the Arctic and the Antarctic to have these phenomenal extreme warm intervals? Is there something that preconditions that? So that's an area of research that we're working on right now. So let me summarize just a couple of things here to wrap up. First, high resolution record in the Arctic comes from Lake Elgagikkan. And you know, I'd like to think there's another Lake Elgagikkan somewhere that we could drill to compare with it. But I'm afraid this might be it. It's a phenomenal record. I'm so lucky that we were able to get the funding and the backing to actually go collect it and continue to analyze it. We have super interglacials that are telling us about rapid climate change and about extreme events that we don't really completely understand. These super interglacials may tell us that, in fact, the Earth is actually much more sensitive to climate change than we thought before. We knew that it was sensitive, and we actually may be much more sensitive than we thought. And we can't exactly explain the cause of all these super interglacials, which is what drives science, is to ask new questions and try to find out what is causing this extreme warming. And it helps us better understand what's happening here in our future. And I'd like to end with this. I love this quote here, is that if we don't change the direction we're headed, we're going to end up where we're going. And this has got to be you and me up here. This is temperature of the Earth over time, and we've got to do something to pull it down. Because as we continue to melt both the West Antarctic ice sheet and the Greenland ice sheet, sea level is going to rise. And unfortunately, it's not reversible. So we've really got to do something to slow it down. And this is going to take all the nations in the world to do this. And I hope that we can bring science and policy together to make those kinds of changes. Thank you very much. So I think if we can have the lights on, lights up, we can have some questions. And I want to invite you to come up to the microphone here or to shout loud enough that I'll repeat your question. Any questions? Does anybody want to know why was CO2 at 400 parts per mil 3 million years ago? Yes. I mean, I think this is it's a real important issue. If we're at 400 parts per mil now, why were we there in the Pliocene? Well, the truth is, if you go back to the time of the dinosaurs, 65 million years ago, we may have been at 2,000 or 3,000 parts per mil. The entire world was tropical. And as we continued to change with continental drift, as you know, as with tectonics, we had mountain building events that built the Himalayas, built the Rocky Mountains and so on. And as you build mountains, you start to wear them down. And the process of weathering silicate minerals actually takes carbon dioxide out of the atmosphere to make clay minerals and so on. So we call it the rock weathering thermostat, that as we were coming from this tropical world and building mountains, we were actually driving CO2 down because of this rock weathering thermostat. So as we came down from, say, 1,000 parts per mil down through where we were, through the Pliocene, we were in that range of 400 to 350 parts per mil. So we were coming off of a very high in the Cretaceous down through to the present as we continued to weather and bring down CO2. So it's actually part of a very long process. And that's why what we've done is we've, in the last 100 years, we've put ourselves back into the Pliocene very quickly with the atmosphere. So anyway, first question.
So what about the planet wobbling, and how is that going to fit in with our CO2 generation human caused?
Yeah, so the changes in Earth's orbit are happening on extremely long time scales. So we have the changes in the eccentricity of the Earth, or in other words, the shape of the Earth's orbit. It's on 100,000 year time scales. And then if you look at the tilt of the Earth, that varies between 21 and 24 degrees. That varies on 41,000 year time scales. And then we have the season in which we're closest to the sun happens on 2019 to 20,000 year time scales. So what's happening now is nothing to do with the Earth's orbit. It's really all about carbon dioxide. So when someone argues that you haven't taken into account the Earth's orbit, it doesn't matter, because what we've done in 100 years is much more radical, because these orbital forcings are happening on much longer time scales. So ideally, if we hadn't put any more CO2 into the atmosphere, even starting 8,000 years ago, we would be sliding into the next ice age, actually. Next question? Yeah.
I've kind of two questions for you. First, how much of your record is recording the polar amplification? And kind of associated with that,
right.
You see gradual changes in CO2, like you were just talking about, but the changes you see in your record seem very abrupt. Right.
Okay. So two questions. The first one was the polar amplification. Absolutely. So we're seeing pretty extreme, that's why we're trying to compare the Arctic with the Arctic, so it's not apples and oranges. And our proxies, because our proxies are naturally very summer oriented. So that's what's very clear. When I show you that temperature of the summers, it's the mean temperature of the warmest month, because we can't exactly back out the cold of the winter, right? I do have a wiggle for that, but I'm not sure, we're not really, it's not probably as precise. So you're right, what we're doing is looking at a polar amplified signal. So we're looking at temperatures that were 6 to 8 degrees warmer than today, which is, if you think about it, the global mean temperature that most people have reconstructed for the Pliocene, say 3 million years ago, was global temperatures were 2 to 3 degrees warmer than present. But in the Arctic, it was much warmer. So those data I'm showing you are, in fact, these amplified temperatures. So that's a good point. The second one is that the smooth CO2 curve is only because to get the analytical, to do the chemistry, to get really high precision is tremendous amount of work, so that we're relying on the biogeochemists to come up with these very detailed carbon dioxide measurements. And I know there's an army of people right now that are trying to get much more highly accurate data on shorter time scales. And then those smooth curves will become much more, they'll vary much more wildly probably, and then we can compare how those changes respond. There are a couple of teams working particularly on some sections in the Pliocene right now, and we're really eager to see what their data produces. But largely it's just very labor intensive to do this work. Yeah.
Thank you. I was wondering, how far back are there proxies for carbon dioxide percentage in the atmosphere and also for atmospheric pressure? Anywhere in the world?
Wow, let's see. I would say most of this, there are CO2 records that go back. I'm just trying to think of the IPCC records, at least 5 million, but probably farther back. There are some estimates that go back, I think, Ed, you can correct me, Eocene? Yeah, Eocene, 55 million years ago. There's some records that, very few, but there are some estimates for that. About atmospheric pressure, I would not answer that.
I think the answer there is there's no good proxy.
Yeah, we don't have a proxy for atmospheric pressure.
Some guesses.
Yeah, right. But there are a couple of really interesting papers that go back at least to the Eocene, so 55 to 60 million years and a little bit farther back. There was a major warming event 55 million years ago called the PETM for short, when there seems to have been a massive outburst of CO2 in the atmosphere, which caused a collapse of the ocean life. And it's happening at the same time scales that we're working on now, so today. So people are studying that. So there are some estimates back then.
Thank you. So this climate issue in my mind has 3 sets of questions. First one is it getting warmer? 2, have we caused it? And the third one is it bad for us? So we all know now it's pretty much your evidence shows it is getting warmer. Do we have a hand in it? Probably yes. And the third one is it bad or good for us? Or bad or good for us?
Yeah,
so,
right. You know, yeah, we struggle with that. So the Earth is warming, and it's warmed naturally before. There's no other explanation for us going to 400 parts per mil, and that's a direct, the warming of the planet is a direct response of that. It's kind of physics, and a lot of people, maybe even congressmen, don't understand it. That's pretty simple. It's going to warm as we increase CO2. There's no question about that. Is it bad for us? There are going to be winners and losers in this as we go forward. My personal concern is about sea level rise. We have a lot of very poor countries and that are very close to sea level. Many of the islands in the South Pacific, parts of Bangladesh, even the Nile Delta, New Orleans, you can name a few, that are really going to be in trouble because sea level is rising. And I think the longer we deny it and don't really deal with the sea level issue, we're just what's the phrase, kicking the ball down the road to the future. So my personal concern is sea level rise. I think that we're going to see larger increases in health issues. In fact, I ran across in my office, I was cleaning my office, and I found an old book from 20 years ago. And in that book, it was talking about health issues. It said something about equine encephalitis coming from southeast US and moving northward into New England. Well, guess what? Last year, we had our first cases of equine encephalitis in New England. I mean, it was forecast, it's coming. We've got all these kinds of things moving northward, just as predicted. And, you know, so with increasing CO2, a lot of ragweed and other things produce a heck of a lot more pollen. And so those are causing some more health issues. So I'm concerned about that. Who are the winners in this? Okay, if you ship goods from China to Europe, and you want to go across the Arctic Ocean, you win because it's a shorter trip. Is that worth it? I'm not sure. You know, so if you want to start growing corn in parts of Canada where you couldn't grow it before, that you might be a winner. Certainly Russia wants to be a winner. They've got a lot of places they'd like to warm up. So there are winners and losers in this. My personal concern in my mind is really the sea level rise and not preparing for it. It's going to take less and less of a storm. As sea level rises, it takes less and less of a storm to do the same damage as we saw in Hurricane Sandy. And that cost us $50-some billion. We can't afford that all the time. And so we do need to do something. You may realize, and you know, was it North Carolina and Florida, and you're not allowed as a state employee to even mention sea level rise. People have been in trouble for that. Now, what nonsense is that? We've got to, parts of Florida, even a few miles inland from the coast, are being saturated with salt water. The roads are flooding with salt water because it's coming up through the porous limestones of Florida. So that you don't have to erode the coastline back. The sea level's coming up from underneath. The same thing is happening in Honolulu, Hawaii, other areas of the world where sea level is coming up. So what are we going to do as this happens more? We've got to start thinking about managing that change. And let's not look at that as gloom and doom. That sounds pretty dire. But I mean, we really have to train young people and people in the universities now. Let's think about coastal management. Let's think about the social change that needs to happen. Let's think about changes in, particularly even the insurance industry is very interested in this prognosis. So there's a tremendous job potential for, instead of white collar jobs, instead of blue collar jobs, let's have green collar jobs, right? Where people are thinking about a green environment and changing the world and making it better and getting people out of harm's way. So, good and the bad.
Any other questions?
Does the high latitude climate record suggest some areas in the high latitudes that might be refuges for Arctic ecosystems that we should be thinking about now?
Yeah, there's been a thought about Arctic refuges, particularly organisms and ecosystems that are surviving on sea ice. And if you look at some of the climate models, if we start to continue in the summer to lose more and more of the sea ice, where are those particularly large mammals like polar bears, where are they going to go, and the sea and the walrus and so on? And one thought is that northern Canada along the Ellesmere Island and Greenland, that would be a last refugia. And you may have heard that 2 men lost their lives about a couple weeks ago out to map that sea ice, and in fact it was a heck of a lot thinner than they thought, and they both went through the ice and their sleds were just found. But they were mapping with an effort to try to define that refugia. And I think it tells us that, in fact, there may not be that kind of refugia. But let me add a note to that. There is scientific evidence, there's geologic evidence that shows that, in fact, maybe 8,000 to 9,000 years ago, there was a period of time when there may not have been any summer sea ice. And it was because of the orbital forcing. And we had almost 7% increase in insulation in the high latitudes. So seals and walrus and those things, these guys have lived through this before. They didn't go extinct. But the difference is that we're up there with them now. And that's the different kinds of pressure. So there are times when these organisms have lived through times when less sea ice. But the decrease in sea ice now is because of us, and we're also implicated in changes in their habitat, and that's what's very different. And we've done this very quickly. That's the other thing, is if you look at 8,000 to 9,000 years ago, the rates of change of the loss of the sea ice happens over thousands of years. What we're doing is something in 100 years, and that's very different. And we don't know how the polar bears will react to that. Anyone? Yeah?
I know relative to the geologic scale, the human presence on the planet is relatively small. Do you typically use the Industrial Revolution as the marker for, mark on the geologic record, or as your, the reference point to our climate?
We tend to use the beginning of the Industrial Revolution because of the steam engine and carbon, mechanisms for cars and so on. And you can see that very clearly in the ice core records. But if you look at, Bill Rudiman has some really interesting papers that he's put forward where he's looking at the expansion of human farms, particularly in growing of rice paddies, that he thinks you can see the impact of the methane and so on from the expansion of humans even as far back as 8,000 years ago, 8,000 to 6,000 years ago. So he's been exploring that over time. Not everyone agrees with him, but he makes the point that if you really zero in and look in very detailed at the carbon dioxide of the atmosphere, you can actually see that when they had the Black Plague and so many people died, that the forests or the fields that were in agriculture became forests again, and you pulled down CO2 a little bit until agriculture started back up again. Again, that's the kind of an area of lots of debate, but it's pretty an interesting phenomenon that he can, that in fact we can actually see the human impact on our atmosphere starting many thousands of years ago.
Do you know where he pulled those, did he take samples from that specific area, or?
No, he's simply looking at the archaeological record of these plagues and land use over time from archaeological records, and then comparing them to the ice core records in particular. Plagues and, what's the name of that?
Those words are in the title, I don't remember.
Plagues and, anyway, Bill Rudiman, check, if you Google him and use Bill Rudiman plagues, you'll probably get it. Not that he's a nice person, he's not a plague. There's a question in the back here?
A long time ago, Sherwood Rowland did a lot of work on the impact of chlorofluorocarbons on ozone, and he was here at OSU maybe 6 or 7 years ago and expressed the concern that climate change may not be rheostatic. We might reach a certain set point or threshold where everything changes very rapidly and irreversibly. Do you have any comment on that?
Boy, I'm not familiar with that exact topic. But certainly, abrupt climate change and surprises is a big issue. That in fact, there may be tipping points in our system. And that's what we're trying to learn from the paleo record is, are there tipping points that we can recognize in the paleo record? And I think that there are, certainly. One of them, we may in fact actually be in a tipping point right now with the loss of sea ice in the Arctic. That may be an important tipping point. But on the chemistry of the ozone layer, I'm not going to try that one. I'm not familiar enough with it. I don't know, Ed, you familiar with that?
I'm not sure he was connecting the two ideas, actually. But
No, he wasn't connecting the two ideas.
Okay, okay. Certainly there, you know, this is such an active area of research, and it's fascinating just to try to figure out, you know, what are we causing and what's changing more quickly that we didn't realize, and it's just a fascinating field. So those of you who are graduate students, I hope you have a lot of work ahead of you, because there's so much more we don't understand, and really fascinating questions to go forward with. Do you want to?
okay, thank you very much.